Above our skies, in the silent dark, something extraordinary is happening. A mysterious new object has been spotted racing toward the sun, as if locked in a cosmic competition with the famous interstellar visitor, 3IATLAS. It comes from beyond our solar system, a traveler from the unknown, carrying secrets written across millions of years of galactic drift. Is it ice and dust, like a comet that will flare into a glowing tail? Or is it a rocky fragment born in another system, slipping quietly past us? In this video, we'll follow its journey, step by step, as the sun's gravity bends its path and the solar wind tests its strength. Along the way, we'll uncover what scientists already know, what they still don't, and why every interstellar visitor is a rare and precious messenger from the stars. This is the Science Pulse, calm storytelling, steady pacing, and awe-inspiring truths about the universe, designed to relax your mind while expanding it. If you enjoy drifting into rest while traveling through the cosmos, subscribe and join us on this gentle voyage. Now, let's settle in, breathe deeply, and trace the path of this cosmic racer into the light of the sun. The cosmic race. Imagine, if you will, a race taking place in the vast emptiness of space. A race where two celestial objects hurtle toward the sun, drawn by its immense gravitational pull. One of these objects is a known visitor, the famous comet 3IATLAS, and the other is a newcomer, a mysterious object that has suddenly entered our solar system. This object, though recent in its discovery, is already racing towards the sun at a speed that has left astronomers in awe. The question that arises is, what is this new object, and what does its journey mean for our understanding of the universe? In the cold depths of space, where objects are isolated and detached from the rhythms of our daily life, such an event might seem distant. But for those who study the stars, this is a moment of immense excitement and potential discovery. As this new object speeds toward the sun, it raises fundamental questions about the origins of celestial bodies, the behavior of interstellar visitors, and how our solar system continues to surprise us with its vast mysteries. This object isn't just racing to the sun, it's racing into our imaginations, stirring curiosity and wonder about what lies beyond our planet's confines. In this chapter, we will explore the cosmic race taking place, examining how this object was discovered, how it compares to the infamous 3IATLAS, and why its speed and trajectory are of great interest to scientists. Along the way, we'll learn about the forces at play, the science behind the object's paths, and what this discovery could mean for future research. By the end of this chapter, you'll understand not only the specifics of this cosmic race, but also the larger questions about the nature of our universe that it raises. The sun's gravitational pull, a key player. To understand why this race is so important, we first need to understand the role the sun plays in shaping the behavior of objects in our solar system. The sun, at the heart of our system, exerts a gravitational pull on everything in its vicinity. This force is what keeps the planets, moons, asteroids, and comets in orbit around it. Gravitational pull is a force that attracts objects toward one another. In the case of the sun, it is so strong that it influences everything within the solar system, pulling objects toward it. This gravitational attraction is what keeps Earth in its orbit and prevents it from drifting off into the vastness of space. It also plays a pivotal role in the movement of comets and other objects that enter the solar system from interstellar space. The gravitational pull of the sun is not just important for maintaining the orbits of planets. It also dictates the trajectories of interstellar visitors, such as comets and asteroids. When an object from beyond our solar system approaches the Sun, it is affected by the Sun's gravity in complex ways. The object's path is altered, and its speed is increased as it is drawn closer to the Sun. This phenomenon is why some comets, like 3IATLAS, appear to travel in highly elliptical orbits that bring them close to the Sun before they are flung back into the deep reaches of space. In the case of the new object racing toward the Sun, its speed and trajectory are governed by this very same force. However, what makes this object unique is its incredibly high velocity. It is moving faster than most comets, and this speed has caught the attention of astronomers who are eager to learn more about it. The discovery of the new object, an astronomical surprise. Astronomers first became aware of the new object when it was spotted by a sky survey, a type of astronomical observation that scans large areas of the sky for moving objects. These surveys are crucial for detecting objects that may be on a collision course with Earth, or that could provide valuable insights into the composition of interstellar space. The discovery of this object was somewhat unexpected. It wasn't initially on anyone's radar, and its high speed raised questions about where it came from and what it could teach us. Scientists quickly realized that this object was different from many other comets and asteroids. They suspected that it might be an interstellar object, just like 3IATLAS, but its exact origin remained a mystery. What made this discovery even more intriguing was the object's speed. It was racing through space at a velocity that outpaced many other objects in the solar system. This made it a perfect candidate for further observation. As telescopes trained their sights on the object, astronomers began to gather more data about its trajectory, its composition, and its potential significance. 3IATLAS, the interstellar visitor. In order to fully appreciate the significance of the new object, it's important to briefly revisit the story of 3IATLAS, the first known interstellar object to pass through our solar system. Discovered in 2017, 3IATLAS was a comet that came from beyond our solar system. Its discovery marked a historic moment in astronomy, as it was the first confirmed object to come from outside the solar system. 3IATLAS's journey through the solar system captivated astronomers and the public alike. The comet's unusual orbit and its fast movement through space made it a subject of intense study. As it neared the Sun, 3IATLAS began to disintegrate, shedding gas and dust in a beautiful display of cosmic wonder. This process, known as outgassing, is typical of comets as they approach the Sun, where the heat causes their icy cores to vaporize. The significance of 3IATLAS wasn't just in its beauty. It provided astronomers with a unique opportunity to study an object from another star system. The data gathered from this comet has been invaluable in understanding the composition of interstellar objects and the nature of the space between stars. It also raised the possibility that other interstellar objects could pass through the solar system in the future, offering more chances to study the cosmos beyond our immediate neighborhood. Now, with the discovery of a new object racing toward the Sun, scientists are eager to see how this new arrival compares to 3IATLAS. Could it be another interstellar visitor? What can it tell us about the space between stars and the forces at play in our galaxy? The object's speed, faster than the rest. One of the most striking features of this new object is its speed. It is moving incredibly fast, much faster than most comets and asteroids that enter the solar system. The high speed of this object has made it a subject of great interest for astronomers, as it could offer important clues about the nature of interstellar objects. To put the speed of this object into perspective, Most comets that come from the outer reaches of the solar system move at speeds of about 30 kilometers per second. However, this new object is moving at a speed of over 100 kilometers per second, a velocity that is far above the average for typical solar system objects. This increased speed means that the object is likely to pass through the solar system much more quickly than other comets. What does this speed tell us? For one, it suggests that the object is coming from far outside the solar system, potentially from another star system. The high velocity could indicate that it has been traveling through interstellar space for a long time, possibly for millions of years. As it nears the Sun, its speed is being further increased by the Sun's gravitational pull, creating a dramatic cosmic encounter. The path to the Sun, what we can expect. As this object races toward the Sun, it will follow a path that is influenced by the Sun's gravity. This path will likely be an elliptical orbit, meaning the object will pass close to the Sun before being flung back out into the depths of space. The exact trajectory of the object will be closely monitored by astronomers, who will use its movement to calculate its speed, origin, and potential future behavior. Interestingly, this object will not be the first interstellar visitor to pass through the solar system, but it may be the fastest. Its close approach to the Sun will provide valuable data about the effects of solar gravity on interstellar objects. Astronomers will also be able to study the object's behavior as it interacts with the Sun's radiation, which could help them understand how objects from other star systems are affected by the Sun's influence. As the object draws closer to the Sun, scientists will continue to monitor its path and gather data. This data could lead to new discoveries about the nature of interstellar objects and the conditions that exist in other star systems. Conclusion: a new chapter in cosmic discovery. The discovery of this new object racing toward the Sun marks an exciting moment in the field of astronomy. Its high speed, its potential origins, and its journey through our solar system raise fascinating questions about the universe and our place in it. As we continue to study this object and its path, we gain a deeper understanding of the vastness of space and the many mysteries it holds. In the chapters that follow, we will explore more about this object's origins, its composition, and what scientists hope to learn from its brief visit to our solar system. We will also examine the significance of its discovery and how it fits into the larger context of our understanding of the cosmos. For now, as we gaze up at the stars, we can take comfort in the knowledge that the universe is constantly surprising us, offering new mysteries and challenges for us to explore. And with each new discovery, we come a little closer to understanding the true nature of the cosmos. Picture the Sun not as a fiery disk in the daytime sky, but as a silent, invisible well carved into the fabric of space. Everything that strays too near slides along its sloping sides, quickening as it descends, slowing as it climbs away. The planets circle the rim in patient loops. The comets swoop down glittering like snow shaken from some ancient eve. Dust and starlight drift toward the center and then are swept aside by light itself. In that quiet mental image, you can feel why this race toward the Sun is a race at all. The finish line is not a place. It is a depth, a minimum, a closest brush called perihelion, beyond which nothing needs to be louder than gravity for motion to change, for ice to steam, for secrets to unfold. The newcomer we are following and the storied traveler called 3IATLAS are both sliding into this well, each taking a different line, each answering the same ancient call. Gravity is often explained as attraction, and that is true enough for a first glance, but for this calm passage, let it be a slope. The deeper you go into the slope near the sun, the faster you must travel to keep from falling straight in. The shallower you are, the gentler your speed can be. When an interstellar visitor comes in from far outside, it does not begin motionless. It carries a memory of its far home in its speed, a little surplus called the excess. Long before the sun can tug strongly, that excess already tells you the visitor was never bound to our star. A bound comet from our own far cloud begins with almost no surplus. It drifts in and is gathered. An unbound visitor begins with a surplus and refuses long-term capture. You can imagine the difference the way water beads on a leaf. A bound drop clings and wanders before it finally slides. An unbound bead skates across and is gone. As the newcomer glides down the slope, it traces a shape that could be a long, thin ellipse if it were bound, or, as in the case of an interstellar object, a hyperbola, open-ended, the mathematical figure of a flyby. That shape is not a choice. It is written from the first moment of approach by the angle of entry and the surplus of speed. If you could stand very far above the page of space and draw only the curves, you would see our planets as nested ovals, and these strangers as open wings passing through, bending just once as if to bow to the sun, and then to continue on. Where the curve tightens most, at perihelion, the speed peaks. Even a slow traveler can be quick there. Even a quick traveler like our newcomer becomes quicker still. The sun does not grant speed for free. It trades it for direction. In return for that bright swing by, the path is turned, and the object leaves pointing somewhere it had not intended when it began. Close to the sun, other forces become textured and personal. Light is not only brightness, but pressure, the subtle push of countless photons striking grains of dust, and the thin skins of gas that boil from a warming nucleus. That pressure is not random. It always streams outward, so small particles are blown away like chaff, building tails that align with sunlight and solar wind, delicate banners of sublimated ice. Along with the push of light, there is the slow friction of radiation that eats at moving dust, drawing it sunward over ages in a quiet rain called Poynting-Robertson drag. For a visitor racing through, that long rain is too slow to matter much, but you can sense it in the behavior of fine debris, a soft nudge toward simplicity that cleans the inner reaches of the system, grain by grain. The solar wind, a breath of charged particles from the sun's corona, shapes those banners too. Invisible and constant, it curls magnetic fields around the traveler's coma and stretches ion tails into straight, pale spears that ignore the curve of motion and obey the electric skeleton of interplanetary space. The wind carries whispers of storms, flares and coronal mass ejections that can thicken those tails, pinch them, or snap them into ribbons that heal in minutes. For a sleeper listening to space as if it were rain on a roof, the wind's effect is a soft clatter on the eaves, a change in the rhythm of drops when a gust comes through. Yet gravity remains the metronome beneath these textures, and its simplest truth is this: the closer you go, the more you must do to remain high. Earth keeps its height by circling at a steady 30 kilometers per second, because the slope at Earth's distance requires that much sideways speed to avoid tumbling in. Mercury moves faster because it is lower on the slope. The newcomer will move faster still at perihelion because it will be lower than Mercury, lower perhaps than any planet, skating through a part of the slope where speeds are astonishing. This is why the race toward the sun is also a race toward clarity. The closer the object gets, the faster it moves, the brighter it becomes, the more it speaks in reflected light and vapor, and the more we, with our patient telescopes and attentive software, can learn. There is a useful, quiet equation that astronomers use to predict this dance, the vis-viva relation, a small, elegant sentence that says a body's speed at a distance depends on that distance and the size of its orbit. You need not write it down to feel what it means. Distance sets the steepness of the slope, and the orbit's shape tells whether the traveler is bound or free. In the newcomer's case, the orbit is a one-time story. The shape is open, and far away from the sun, the speed settles back to its surplus, the bare minimum it needs to stay a wanderer between stars. Near the sun, the same relation says the speed must rise in answer to the deepening slope. We will not fill this quiet with numbers. We will fill it with the sense that every approach and retreat is measured by a calm, impartial rule that does not change. Not every motion in the inner solar system is gravity alone. Comets are not stones. They are riddled with ices that release gas when warmed. That gas jets from the surface, sometimes in fountains from pits or cracks, sometimes evenly in a global whisper. Each jet is a tiny rocket, and tiny rockets have consequences. They push back, and that push can add a little to the comet's speed, or steal a little, can tilt the path by less than a whisper, and yet that whisper repeated over days and weeks can shift where the traveler will pass by. To astronomers, these are non-gravitational accelerations, a tidy phrase for the friendly complication that comets bring. They are reminders that bodies are bodies, not just points in equations, that they rotate, that they have day and night sides, that they wake up when warmed and sleep again when cooled. In the deeper background of this simple story sits the structure of the solar system itself. Long ago, heavy planets stirred the outskirts the way a spoon stirs honey, sending some small bodies inward to become comets and others outward to be lost to the night between stars. That slow stirring never stopped. Jupiter in particular is a conductor in this orchestral hall. A pass near the giant can turn a neat loop into a new loop, can shorten a yearling comet's period or send it out for centuries, can tweak a path the way a fingertip on a spinning coin alters where it comes to rest. For an interstellar visitor that does not loiter, Jupiter's power is more like a chance meeting in a crowded station, a jostle that bends a shoulder and changes the angle of exit by a few degrees, enough to aim the stranger toward a slightly different future. The inner planets also have gravity, of course, but their role is usually to watch and to reflect. A close approach to Earth or Venus can provide a second, smaller swing-by, a tug that trims or dares the path to approach a fraction closer to the Sun. These planetary encounters are not common for a single passage, but each is mapped in advance by careful watchers. There is a tender, practical reason to do this. We look after our own house. For nearly every visitor, the outcome is unremarkable, a pass behind a planet at a distance that is safe even for the faintest satellites. But the mapping that keeps us calm is the same mapping that makes discovery. We learn where to point the lenses, when to listen for gas, how to tilt the spectrograph to catch the lines of water and carbon monoxide and cyanide etched in starlight. All of these motions occur in a frame that is not entirely rigid. Space near the sun is curved just a little more than Newton's fine slope predicts, a tiny correction from relativity that shows itself in the slow precession of Mercury's orbit and in the way light itself in a close pass bends and delays by nanoseconds. For a fast visitor tickling the inner regions, That extra curvature is a trace on the path so small you need exquisite attention to see it. Still, it is there, a fine embroidery around the edge of an already elegant cloth, reminding us that the sun is not only mass and light, but the sculptor of space. When we say the newcomer is racing 3IATLAS to the sun, we are using a friendly metaphor to organize our calm curiosity. In truth, they do not care about one another. They are travelers on two different lanes into the same valley. Yet the comparison helps. 3IATLAS carried its own surplus, entered on its own line, and left with its own secrets half revealed and half kept. The newcomer has a different surplus, a different angle, a different minimum distance. Those small differences write different stories in gas and dust. One may awaken earlier, shedding a broad, gentle coma at a large distance. The other may remain quiet until deep in the inner system, and then burst with sudden, short-lived jets. One may break under thermal stress as old fractures widen. The other may be compact and hold. These are not competitions so much as rhymes. Each verse adds a word to the language we use to speak about interstellar ice, about the glues and grains and lacquers that form in the long cold between stars. There is a human rhythm to this too, and it is worth naming here because the sun's gravity does not act on instruments or plans, only on bodies, and yet the bodies are known by the instruments and plans. A discovery alert goes out. Observatories schedule time between weather and other priorities. With each clear night, the newcomer is measured again, and the line of its path is tightened the way a pencil line is darkened by tracing. Amateur astronomers contribute with sensitive cameras and careful reductions. Space telescopes, if schedules and orientations allow, tilt slightly to catch a spectrum above the interference of air, revealing not only that gas is present, but which gases and in what ratios. Theories of formation and alteration are quietly tested. Is the carbon monoxide to water ratio typical of distant solar comets, or does it suggest a colder nursery under a dimmer star? Are there grains of sodium in the tail, a sign of rock heated to incandescence, or is the tail purely molecular, a sign of gentle warming? The sun's gravity does not answer these directly. It provides the stage light that makes the answers visible, and we collect them like dew. As the newcomer sinks lower on the slope, the meaning of race softens into a measured anticipation of the minimum. Perihelion is not only the point of closest approach, it is the point of maximum change. Speed peaks there, yes, but so do rates of transformation. Crusts that were rigid at Jupiter's distance grow porous as trapped gases expand. Dust that clung in low gravity spills into space to form a veil whose thickness depends on how firm the surface was to begin with. If there is a spin, jets can act like tiny thrusters and alter it, quickening or slowing the rotation, changing day length by minutes or hours in a single week. In the most dramatic cases, the stress is too much, and the body breaks into two or more pieces, each a little world with its own new day-night cycle and its own new jets. Even this is not disaster in the language of comets. It is renewal, the revealing of interiors that have not seen starlight since they formed. Some listeners worry when they hear racing to the sun, as if there is a possibility of falling in and feeding a catastrophe. The quiet truth is that this valley is steep but shallow compared to the sun's own scale. Even a close pass is no gulp. The sun will not notice. These are not stones thrown into a pond. They are gnats passing through a cathedral. The warmth and light make the passage vivid for us, but the star continues in its cycles, cycling its magnetic field, breathing its wind and ringing with pressure waves from within. The visitor is a letter arriving at a house that is older than the letter and will remain after it has been read. And what of the path out? After the minimum comes the climb. Speeds drop as the slope shallows, and the newcomer trades velocity back for height. The open curve is symmetric in time if you focus only on gravity, but the tails and jets and tiny thrusters of outgassing make the story asymmetric. Material is lost, the mass is lighter, the spin is changed. The face that was night on the way in becomes day on the way out, and the reverse, so solar heat paints the two halves differently. A spectrograph taken after perihelion is not the same as one before, and that difference is a final gift. We read the before and after as a pair and build a small biography. What was trapped, what was freed, what the grains looked like, how the crust behaved, which parts were most fragile. For a bound comet, this biography continues on a later return. For an interstellar visitor, there will be no return. The book must be read on the first and only pass, and so we read slowly and attentively. This is perhaps the gentlest reason to think about the sun's gravity at bedtime. It is the quiet guarantee that there is an order to passing things. Strange objects can appear from beyond our familiar streets, but when they do, their footfalls on the slope will follow a pattern that has not changed since patterns were first possible. If they carry mysteries, those mysteries are coaxed into visibility by warmth and light and the deepening of the well, and then the travelers go on, and we are left with the memory of their swing and the notes we took during their visit. The slope has not moved. The well remains. There will be other travelers, other open curves, other veils of dust that glow briefly and then thin and are gone. So, the phrase "racing 3IATLAS to the sun" is not an alarm. It is an invitation to watch two lines draw themselves on a page and to feel, for a few weeks or months, the patience of a star and the restless curiosity of small things that have journeyed far. It is to learn that speed near the sun is not recklessness, but a necessity, a response to the steepness of the slope, and that the very steepness that quickens them also warms them into speaking. Gravity, the shape of the well, is the quiet narrator of this tale. It does not raise its voice, it simply deepens toward the center, and everything else, a tail unfurling, a nucleus turning, a faint shift in path from a jet awakened at dawn, follows from that one simple fact. If you step back from the details and look at the whole, there is a soft symmetry to comfort you to sleep. From far away, the newcomer seems slow and faint. As it descends, it brightens and hurries. It reaches its singular moment of closeness, flourishes a tail, perhaps whispers a bit of inner composition, then fades and slows as it climbs back to quiet. In that arc, you can hear a breath drawn in and let out, a rise and fall that makes a lullaby of orbital dynamics. The sun's gravity has sung this lullaby to every small traveler that has ever come near it. Tonight it sings to a newcomer and to an old guest whose name we have learned, and to us, who are also on a babe curve around the well, lulled not by danger or drama, but by the assurance that in a universe so wide there are patterns gentle enough to learn, and that learning them, together, calmly, is its own kind of rest. The vastness of the cosmos is an astonishing concept. It's easy to forget, standing on Earth with the clear blue sky above us, just how much space stretches between the stars. But when we consider the movements of objects through our solar system, like the newly discovered object racing towards the sun, we are reminded that there is more out there than we can possibly comprehend. The journey this object has taken to get here, and the trajectory it will follow as it continues its path, is both a mystery and a marvel. For scientists, each new discovery like this one offers a fresh puzzle, a piece of the greater cosmic picture that continues to unfold with every new observation. In the case of this object, its trajectory is of particular interest. The path it is taking through our solar system, its speed, and the way it interacts with the sun's gravitational field are all clues that can help us understand more about the dynamics of interstellar space. But before we can dive into the specifics of its journey, it's important to first explore how this object was discovered. How, despite the immensity of space, we are able to pinpoint such objects as they come through our solar system. The search for visitors, how the object was discovered. Astronomy, as we know it today, relies heavily on the use of advanced technology, telescopes, satellites, and computer algorithms, designed to help us peer into the deepest reaches of space. However, for centuries, humanity's view of the universe was limited to what could be observed with the naked eye. Only in the past few hundred years have we been able to develop tools that allow us to glimpse the true scope of the cosmos. And even now, with our sophisticated instruments, the task of discovering distant objects, especially those entering from beyond our solar system, is an extraordinary challenge. This new object, like many others before it, was spotted by one of these advanced sky surveys, designed specifically to scan the night sky for moving objects. One of the most prominent of these surveys is the ATLAS project, which stands for Asteroid Terrestrial Impact Last Alert System. This project uses a network of telescopes to monitor the sky for near-Earth objects that could pose a threat to our planet, but it also provides data on other celestial phenomena, such as comets, asteroids, and interstellar visitors. The discovery of this new object was a bit of a surprise, however. Though astronomers had been monitoring the general region of space it would occupy, they had not expected it to arrive so soon. When it was first detected, its high speed and unusual trajectory immediately raised questions. Was this another interstellar object like 3IATLAS? Or was it something else entirely? Early analysis of its orbit confirmed that it was moving too quickly to be bound to the sun, suggesting that it was indeed an interstellar visitor, just like its predecessor. As the object continued on its path, astronomers refined their observations, tracking its progress and gathering more data. The object's trajectory was carefully mapped, revealing its path and the precise way it was interacting with the sun's gravitational field. This data provided valuable insights into the object's speed, its trajectory, and its potential origin. What's fascinating is how these discoveries unfold. The process of detecting such objects is not like flipping a switch. It's a gradual, careful process. When a new object is spotted, scientists must first confirm that it is not a known object within our solar system, like a distant comet or asteroid. Then, they must determine its speed and trajectory, calculate its orbit, and analyze any available data on its composition. In the case of this new object, all of these factors pointed to the conclusion that it was an interstellar visitor, a fact that continues to excite astronomers to this day. What we know about its speed. When it comes to celestial objects, one of the most intriguing aspects of their behavior is their speed. How fast is the object moving? What does its speed tell us about its origins? In the case of this new object, its speed has been a point of particular interest. As it nears the sun, the object is moving at an astonishing speed, far faster than many of the comets and asteroids that typically pass through our solar system. This speed, which is measured in kilometers per second, is a direct result of the sun's gravitational pull. The closer an object gets to the sun, the faster it will move, as the sun's gravity accelerates it toward its perihelion, the point of closest approach. But what makes this object so unique is that it is moving far faster than the typical comet or asteroid. While many comets move at speeds of around 30 kilometers per second, this new object is traveling at a speed that exceeds 100 kilometers per second, more than 3 times faster. This high velocity is one of the reasons why astronomers were so eager to study it. The speed suggests that this object has come from far beyond our solar system, possibly from another star system entirely. To give you a sense of scale, the fastest known comets within our solar system are those that have been on long elliptical orbits, like the famous Hale-Bopp comet. These comets have speeds that range between 30 and 50 kilometers per second as they move through the inner parts of the solar system. But this new interstellar visitor is moving at more than double that speed, which is what makes it such an extraordinary object. The object's path, a cosmic journey. The path this new object is taking through our solar system is equally fascinating. As we mentioned before, this object is on a hyperbolic trajectory, an open-ended curve that indicates it is not bound to the sun. Instead, it will pass by our star, continue on its journey through space, and eventually leave the solar system entirely, heading off into the unknown. Its trajectory is almost perfectly aligned with that of 3IATLAS, the first confirmed interstellar visitor. However, there are important differences between the two objects. While 3IATLAS was a comet, the new object could be a different type of celestial body, possibly an asteroid or a fragment of a larger body. Its path and composition will be studied in greater detail in the coming months and years as it continues on its journey. The new object's path also provides an intriguing opportunity for scientists to study the behavior of interstellar objects as they pass through our solar system. How do these objects interact with the sun's gravitational field? How do they respond to the solar wind and the light pressure exerted by the sun? These are questions that could reveal important information about the conditions that exist in interstellar space, as well as the processes that govern the movement of objects in our galaxy, theories about its origin. As with any discovery, there are questions about the object's origins. Where did it come from? What could its composition reveal about the regions of space it has traveled through? These questions have sparked a great deal of speculation among astronomers. One of the leading theories is that the object originated from a distant star system, possibly one located in the outer reaches of the Milky Way galaxy. The fact that it is moving so quickly suggests that it has been traveling through interstellar space for millions of years, possibly since the early days of our galaxy. Its composition, which will be studied in more detail as it passes closer to the sun, could provide clues about the conditions that exist in other star systems. Another theory suggests that the object could be part of a much larger body, possibly a remnant of a larger planetary system, that was disrupted by the gravitational forces of a nearby star. If this is the case, the object could provide valuable information about the formation and evolution of planets and stars in other parts of the galaxy. The importance of this discovery. The discovery of this new object racing toward the sun is more than just a scientific curiosity. It is an opportunity to gain deeper insights into the nature of our galaxy and the objects that inhabit it. Each new interstellar object that passes through our solar system is a reminder that we are not isolated in this universe. We are part of a vast, interconnected cosmic network, and the objects that travel through our solar system are like messengers from distant parts of the galaxy, carrying with them clues about the conditions and events that shape the stars and planets around us. For astronomers, this discovery is a chance to study the behavior of interstellar objects in greater detail than ever before. The data collected from this object's path will be invaluable in refining our understanding of how objects from other star systems interact with the sun's gravitational field, how they are affected by solar radiation, and what their composition can tell us about the materials that make up the building blocks of stars and planets. In the end, this discovery is a reminder that the universe is full of surprises and that there is always more to learn. As we continue to explore the cosmos, each new object, each new discovery adds another layer to our understanding of the universe and our place within it. And for those of us who look up at the night sky with wonder, there is always something more to marvel at, something more to explore. When we think about the sun, it's easy to imagine it as a single, steady object, a giant ball of fire that illuminates our days and provides the warmth needed for life on Earth. But when you start looking at it through the lens of astronomy, the sun becomes something far more complex. A star that acts as the center of our entire solar system, with its own set of rules, behaviors, and mysteries that govern everything around it. The influence of the sun stretches far beyond the Earth, reaching out to every planet, moon, comet, and asteroid that orbits within its grasp. The sun's gravity, light, and solar wind are the unseen forces that shape everything in our solar system, from the slow-motion dance of the planets to the sudden brief passage of an interstellar object like the one racing toward it. In this chapter, we'll take a deeper look at 3IATLAS, the first confirmed interstellar visitor to pass through our solar system, and how its behavior compared to that of the new object. 3IATLAS arrived in our cosmic neighborhood in 2017, and its visit provided scientists with a unique opportunity to study the behavior of an interstellar object as it passed through the inner solar system. Although 3IATLAS is gone, its legacy endures in the data it left behind, which continues to shape our understanding of what happens when objects from other star systems visit ours. But to understand the significance of 3IATLAS, we must first appreciate why its discovery was so important. For centuries, humanity has looked to the stars with awe and wonder, imagining that there might be other worlds out there, orbiting distant suns. Yet, for all our advances in space exploration and telescope technology, we had never before seen a visitor from another star system. That all changed in 2017, when 3IATLAS was spotted by astronomers using a sky survey telescope in Hawaii. The object was unlike anything scientists had seen before, a comet-like body that was not bound to our sun, but instead was passing through our solar system on a trajectory that would take it out into interstellar space once again. 3IATLAS was, in many ways, a cosmic anomaly. Its orbit was highly unusual, coming in from an angle that suggested it had traveled from outside our solar system, possibly from another star system entirely. And as it passed through our solar system, it did something that comets typically do. It began to heat up as it neared the sun. As the heat of the sun caused the icy nucleus of 3IATLAS to vaporize, the comet began to shed gas and dust, forming a bright, glowing coma and tail. This behavior, known as outgassing, is a hallmark of many comets, but in the case of 3IATLAS, the scale and speed of the outgassing were unprecedented. The comet's rapid movement through the solar system meant that it didn't have much time to lose mass, but in the short time it was here, it shed material that astronomers were eager to study. The scientific community was abuzz with excitement at the discovery of 3IATLAS. For the first time, astronomers had the opportunity to study an interstellar object in real time as it passed through our solar system. And the data gathered from 3IATLAS has proven invaluable in the years since its departure. Not only did scientists learn about the composition of interstellar comets, but they also gained insight into the behavior of these objects as they interact with the sun's gravitational field, the solar wind, and the light pressure exerted by the sun. For a brief moment, 3IATLAS allowed us to peer into the depths of space and glimpse the characteristics of objects that originate from outside our solar system. Now, as we turn our attention to the new object racing toward the sun, it's impossible not to compare it to 3IATLAS. The similarities are striking. Both objects are interstellar visitors that arrived in our solar system from far beyond our neighborhood. Both objects are moving at extraordinary speeds, far faster than typical comets or asteroids. And both objects are traveling on hyperbolic trajectories, meaning they are not bound to our sun and will continue on their journeys after they pass through our solar system. But while 3IATLAS had a clearly defined coma and tail due to its outgassing, the new object's behavior has been more enigmatic. It remains to be seen whether the new object will exhibit the same outgassing behavior as 3IATLAS, or whether it will reveal something entirely different, what 3IATLAS revealed. The true value of 3IATLAS lay not only in the fact that it was the first interstellar object to be discovered in our solar system, but also in what it revealed about the space between stars. Before 3IATLAS, scientists had only been able to speculate about the composition and behavior of interstellar objects. But when 3IATLAS passed through our solar system, it provided the first real data on these mysterious travelers. One of the most interesting aspects of 3IATLAS was its composition. Early observations suggested that it was a carbon-rich object, possibly a fragment of a larger comet or asteroid. This was significant because it indicated that the building blocks of planets and moons in other star systems might be similar to those in our own. The fact that 3IATLAS contained carbon, along with other elements such as hydrogen, oxygen, and nitrogen, suggested that the basic ingredients for life as we know it might be more common throughout the galaxy than previously thought. Additionally, the study of 3IATLAS's trajectory revealed that it was not a random visitor from a distant star system. Its path was highly specific, suggesting that it had been traveling through interstellar space for millions of years before it reached our solar system. This raised new questions about the nature of interstellar space itself. How far do these objects travel, and what conditions do they encounter as they journey through the vast emptiness between stars? Scientists were also fascinated by the fact that 3IATLAS had not been detected until it was already deep within the solar system. This raised concerns about our ability to spot such objects before they arrive. If 3IATLAS had been on a collision course with Earth, we would not have had much time to react. The discovery of 3IATLAS served as a wake-up call to the astronomical community, reminding us that the space around us is far more active than we might realize. Objects like 3IATLAS, and now the new object racing toward the sun, are not as rare as we once thought. They are out there, traveling through the cosmos, and we need to be ready to spot them before they enter our solar system. Comparing the two visitors. Now that we have a better understanding of what 3IATLAS revealed, it's important to consider how the new object compares. As mentioned earlier, the new object is racing toward the sun at an even higher speed than 3IATLAS, making it an even more intriguing subject of study. While 3IATLAS was already a fast-moving object, this new visitor's speed suggests it may be coming from a different part of the galaxy, or perhaps even from a different galaxy altogether. One of the key differences between the two objects is their behavior as they approach the Sun. 3IATLAS began to outgas as it neared the Sun, creating a visible coma and tail. This was expected behavior for a comet, and it allowed astronomers to study the composition of the object's nucleus and learn more about the materials that make up interstellar comets. However, the new object has not exhibited the same signs of outgassing, at least not yet. This could mean that the new object is not a comet at all, but rather an asteroid or some other type of celestial body that doesn't have the volatile ices that comets typically contain. Alternatively, it could be that the new object has simply not yet reached the point in its orbit where it begins to heat up and shed material. Another key difference is the shape of their trajectories. While 3IATLAS followed a relatively predictable path as it passed through the solar system, the new object's trajectory is more complex. It is moving at such a high speed that its path is not as well defined, and scientists are still working to calculate its exact orbit. As the object gets closer to the Sun, its speed and trajectory will be affected by the Sun's gravity, and this will provide more data on how objects from outside our solar system behave as they pass through our cosmic neighborhood. As the vast expanse of space stretches out before us, we are often reminded that the most significant discoveries are not the ones that are easy to see. Instead, they are the ones that we uncover through quiet observation, careful study, and a willingness to look beyond what is immediately visible. When it comes to the study of celestial objects, whether they are distant stars, massive planets, or tiny comets, our understanding is constantly evolving, and every discovery adds a new layer to the mystery of the universe. In this chapter, we shift our focus to the human angle, diving into the lives of the scientists and researchers who dedicate themselves to the study of the cosmos. The discovery of the new object racing toward the Sun, much like 3IATLAS before it, is the result of years of hard work, dedication, and often a bit of luck. But behind every discovery, there are people, astronomers, astrophysicists, and engineers who make it their life's work to answer the great questions of the universe. Through their eyes, we begin to see not only the object itself, but also the excitement, challenges, and rewards that come with working in this field. These scientists are not just watching the night sky passively. They are actively engaged in a search for meaning, trying to unravel the secrets of the universe that lie just beyond our reach. The role of sky surveys. One of the key tools that has revolutionized the way we discover objects like the new interstellar visitor is the sky survey, a systematic effort to scan large portions of the sky in search of objects that might otherwise go unnoticed. Sky surveys have been instrumental in the discovery of many celestial bodies, including asteroids, comets, and other objects that might pose a threat to Earth. These surveys are usually conducted using a combination of ground-based telescopes and, increasingly, space-based observatories, which allow scientists to monitor vast areas of the sky in a relatively short amount of time. The sky survey responsible for discovering this new object is the ATLAS project, Asteroid Terrestrial Impact Last Alert System, which operates a network of telescopes designed to detect potential hazards to Earth. ATLAS is unique in that it not only detects near-Earth objects, NEOS, but also looks for objects that come from outside our solar system, such as interstellar comets and asteroids. The discovery of the new object racing toward the Sun was a direct result of the efforts of astronomers working on ATLAS, who spotted the object as it was entering our solar system. For the scientists working on these projects, the discovery of a new, interstellar object is a moment of profound excitement. The opportunity to study an object from another star system, to gather data on its composition, speed, and behavior, is a rare and invaluable experience. But the excitement is tempered by the understanding that these objects are fleeting. They pass through our solar system quickly, and once they leave, they are gone forever. This makes the work of astronomers both urgent and deeply rewarding. The pioneers of interstellar discovery. Before the advent of sky surveys, the idea that objects from outside our solar system could enter our cosmic neighborhood was more science fiction than science fact. But with the discovery of 3IATLAS in 2017, the scientific community was forced to reconsider its assumptions about the solar system. The discovery was groundbreaking, not only because it was the first confirmed interstellar object to pass through our solar system, but also because it opened the door to a new way of thinking about the cosmos. The team responsible for the discovery of 3IATLAS was led by a group of astronomers at the University of Hawaii's Institute for Astronomy. The astronomer who first noticed the object was Dr. Robert Warwick, a researcher who had been using the Pan-STARRS telescope to survey the sky for potential threats to Earth. When he spotted 3IATLAS, he immediately recognized that it was something special, a fast-moving object that was traveling too quickly to be bound to the sun. Since then, astronomers have been working to understand more about 3IATLAS and what it tells us about the universe. Dr. Warwick and his team were able to track the object's trajectory and determine that it was an interstellar object, likely from a distant star system. This discovery was a major milestone in the field of astronomy, and it sparked a renewed interest in studying the paths of interstellar objects. The new object racing toward the sun is just the latest chapter in this ongoing story, and it promises to reveal even more about the mysteries of interstellar space. The challenge of interstellar objects. While the discovery of an interstellar object like 3IATLAS is an exciting and groundbreaking achievement, it also presents a number of challenges for scientists. One of the biggest challenges is the fact that these objects are often moving incredibly fast, much faster than typical comets and asteroids in our solar system. This high speed makes it difficult to track their movements and gather data on their composition. When an interstellar object enters our solar system, it is moving so quickly that by the time astronomers are able to detect it, the object has already passed through the inner solar system and is on its way out. This means that scientists have a limited amount of time to study the object before it disappears from view. For example, when 3IATLAS passed through our solar system, astronomers only had a few months to observe it before it was too far away to study in detail. To overcome these challenges, astronomers rely on a combination of high-tech telescopes, fast-moving spacecraft, and sophisticated computer algorithms to track and analyze the object's path. The data they gather during the brief window of time when the object is visible is crucial for understanding its composition, origin, and behavior. This is where the new interstellar object racing toward the sun becomes particularly interesting. While 3IATLAS was the first interstellar object to be discovered, the new object offers scientists an opportunity to build on the knowledge gained from that discovery. The object's speed, trajectory, and composition could provide valuable clues about the conditions in other star systems, as well as the processes that govern the movement of objects in interstellar space. The impact of technology on discovery. The rapid pace of discovery in the field of astronomy has been made possible by advances in technology. In the past few decades, telescopes have become more powerful and more sensitive, allowing scientists to detect objects that were previously invisible. Space-based observatories, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, are poised to revolutionize our understanding of the universe by providing clearer, more detailed images of distant objects. But technology has not only improved our ability to see distant objects, it has also enhanced our ability to analyze them. Advances in computing power and data analysis techniques have allowed astronomers to process vast amounts of data and make sense of complex patterns. With the help of machine learning and artificial intelligence, scientists can now identify objects that might have gone unnoticed in the past, and they can track the movement of these objects with unprecedented precision. For the scientists working on projects like ʻATLAS, technology is both a tool and a partner in their quest to understand the cosmos. Without these advancements, the discovery of objects like 3IATLAS and the new interstellar visitor would not be possible. The work of these astronomers is a testament to the power of technology and its ability to push the boundaries of human knowledge. The excitement of discovery. For the researchers involved in the discovery of the new object racing toward the sun, the excitement is palpable. Every new piece of data that is gathered brings them one step closer to understanding this mysterious visitor. But it is not just the science that excites them. It is the fact that they are on the front lines of a discovery that could change our understanding of the universe. The study of interstellar objects is a relatively new field, and every discovery adds to the growing body of knowledge that will shape the future of astronomy. Just as the discovery of 3IATLAS opened up new avenues of research, the discovery of this new object promises to expand our understanding of the cosmos even further. But even beyond the science, there is a human element to these discoveries. The excitement and wonder that come with discovering something new about the universe are shared by the entire scientific community. And it is that shared sense of awe and curiosity that drives astronomers to keep looking up, to keep searching for the next big discovery. In the pursuit of understanding our universe, we often find that the smallest details can reveal the most profound truths. It's easy to imagine space as a vast, empty expanse, silent and still, where celestial bodies drift past each other in their own isolated orbits. Yet, the truth is far more dynamic. Each object that passes through our solar system carries with it a story, one of creation, of forces shaping its destiny, and of conditions unique to the distant corners of the universe from which it came. These objects, whether they are comets, asteroids, or interstellar visitors, are the messengers of the cosmos, telling us not just about themselves, but about the larger processes that govern the formation and evolution of stars and planetary systems. This new interstellar object racing toward the sun, like 3IATLAS before it, is one such messenger. Its speed, trajectory, and behavior as it approaches the sun hold clues about its composition, its origin, and the forces that have shaped it. In this chapter, we turn our attention to the composition of the new object. What is it made of? What can we learn about its building blocks? And what do those building blocks tell us about the region of space it originated from? The mystery of composition. When astronomers first detect a new object, one of the first things they want to understand is its composition. Is it a rocky asteroid, a frozen comet, or something entirely different? The composition of a celestial object reveals much about its history and its origins, and it helps scientists classify it within the broader context of the solar system and beyond. In the case of comets, the composition is relatively straightforward. Comets are typically composed of a mixture of ice, dust, and gas, frozen remnants of the early solar system. When they approach the sun, the heat causes the ice to vaporize, releasing gas and dust in a spectacular display of light. This process, called outgassing, is what creates the bright coma and tail that we see from Earth. However, not all objects that pass through our solar system behave like typical comets. Some, like asteroids, are rocky and don't exhibit outgassing behavior. These objects may also show signs of space weathering, such as the darkening of their surfaces due to exposure to cosmic rays. For the new object racing toward the sun, scientists have not yet been able to determine whether it is a comet or an asteroid. This question is central to understanding the object's composition. If it is a comet, we can expect to see signs of outgassing as it approaches the sun, with a bright coma and tail forming as the heat vaporizes its icy core. On the other hand, if it is an asteroid, we may not see the same dramatic outgassing behavior, and instead, we would focus on the object's surface features and its interaction with the solar wind. The challenge, of course, is that these objects are often very far away when they are first detected, and by the time they get close enough for detailed study, they may have already passed the point where outgassing is visible. This is why the discovery of interstellar objects is so exciting, because these objects come from beyond the solar system, and their composition may differ from anything we've observed in our local neighborhood. The new object, like 3IATLAS before it, provides a unique opportunity to study a sample of the universe's raw material, untouched by the processes that have shaped the planets and moons within our own solar system. Techniques for analyzing composition. To study the composition of an object like this one, astronomers use a variety of techniques. One of the most powerful tools at their disposal is spectroscopy, the study of the light emitted or reflected by an object. When light passes through a substance, it interacts with the atoms and molecules in that substance, causing them to absorb and emit light at specific wavelengths. By analyzing the spectrum of light from an object, scientists can determine its chemical composition, temperature, and other physical properties. In the case of the new object racing toward the sun, astronomers will use spectroscopy to study the light reflected off its surface. This will give them clues about what the object is made of, whether it contains volatile compounds like water ice or carbon dioxide, or whether it is primarily composed of rocky materials like those found in asteroids. If the object is a comet, its coma and tail will also provide valuable information, as the gases and dust released by the object will have their own distinct spectral signatures. Another technique that can be used to study the composition of an object is thermal infrared imaging. This method involves measuring the heat emitted by an object, which can reveal information about its size, shape, and surface composition. By measuring the temperature of the object at different wavelengths, astronomers can identify whether it has a uniform temperature or whether certain areas are heated more than others. This can provide clues about the object's surface features and its internal structure. In addition to these remote sensing techniques, scientists may also use spacecraft to get a closer look at objects passing through our solar system. While no spacecraft are currently on a direct course to intercept the new object racing toward the sun, future missions may be able to send probes to study such objects up close. These missions would allow scientists to directly sample the surface of the object, measuring its composition and analyzing its physical properties in greater detail. What the composition can tell us. The composition of an interstellar object like this one can tell us a great deal about the region of space it originated from. Objects that form in the cold outer regions of a star system, for example, are often composed of ices and gases that have remained frozen for billions of years. These objects may contain preserved samples of the material that formed the star system itself, and studying them can provide valuable insights into the early conditions that led to the formation of planets and moons. In contrast, objects that form closer to their parent star, where temperatures are higher, are typically composed of rock and metal. These objects, known as asteroids, are remnants of the planet-forming process. They are the building blocks of planets, but they were never able to coalesce into full-fledged worlds. Instead, they remain as scattered debris, sometimes serving as the seeds for future planetary systems, or as the remnants of failed planets. The new object racing toward the sun could provide a unique glimpse into the diversity of materials that exist beyond our solar system. If the object is a comet, its composition might resemble that of comets in our own solar system, rich in water ice, carbon compounds, and other volatile materials. If it is an asteroid, its composition might be more rocky and metallic, offering clues about the early building blocks of planets in other star systems. What makes this discovery so exciting is that we are witnessing a rare opportunity to study an object from outside our solar system, and its composition could reveal information about the conditions that exist in other parts of the galaxy. As we study the new object's surface, its tail, if it forms one, and its spectral signature, we may uncover a host of new insights into the materials that make up stars and planets, and perhaps even the origins of life itself. The importance of studying interstellar objects. The study of interstellar objects is not just a scientific curiosity, it has far-reaching implications for our understanding of the universe. These objects provide us with a direct sample of material from beyond our solar system, and studying them allows us to better understand the processes that govern the formation of stars and planets. Interstellar objects like 3IATLAS and the new object racing toward the sun also challenge our understanding of the dynamics of our galaxy. The fact that these objects can travel across vast distances of interstellar space and then enter our solar system is a reminder of the interconnectedness of the cosmos. Our solar system is not an isolated island, but rather part of a much larger galactic ecosystem, where objects can move freely between star systems and provide us with insights into the conditions that exist in other parts of the galaxy. In addition, studying the composition of interstellar objects can help us understand the building blocks of life. Many of the compounds found in comets and asteroids, such as amino acids, hydrocarbons, and water, are considered to be some of the fundamental ingredients for life. By studying the composition of these objects, we can learn more about the conditions under which life might arise, both within our own solar system and in other star systems. As we continue to explore the universe, the study of interstellar objects will undoubtedly play a key role in expanding our knowledge of the cosmos. Every new discovery, whether it's a comet racing toward the sun or a distant planet in another star system, brings us one step closer to understanding the true nature of the universe and our place within it. And as scientists continue to study objects like the new interstellar visitor, they will unlock new secrets about the origins of the universe, the forces that shape it, and the conditions that give rise to life. There is something profoundly humbling about the way the universe presents itself. We, as humans, have created elaborate systems to explore the skies, from telescopes that peer into distant galaxies to space probes that traverse the dark void of space. And yet, every time we think we have a grasp on the enormity of space, we are confronted with something that reminds us of how little we truly know. In this chapter, we will take a step back, and look at the journey of the new object racing toward the sun from a broader perspective. While scientists are focused on understanding the specifics of the object, its speed, its composition, its origin, there is an underlying, deeper significance to its journey. It's not just about the object itself, but about the context in which it exists, the vastness of interstellar space, the forces that shape it, and the way objects like this one travel through the cosmos. This journey is more than a mere passage. It's a story of time, space, and forces that govern the movement of celestial bodies. As we trace the object's path, we find ourselves looking at not just a single moment in time, but a sequence of events that stretches back millions, even billions of years. To understand this journey fully, we must place it within the context of cosmic history. The path through interstellar space. The new object racing toward the sun has traveled a long way to reach us. While we can only observe its path through the solar system for a brief period of time, its journey began long before it was detected by astronomers. It entered the solar system from the far reaches of interstellar space, an expanse so vast that it is difficult for us to truly comprehend. The space between stars is not empty. It is filled with gas, dust, and cosmic rays. But it is so spread out that objects moving through it don't interact much with the surrounding material. As the object journeyed through interstellar space, it traveled at incredible speeds, influenced only by the gravitational forces of distant stars and the faint pressure exerted by the interstellar medium. It is likely that this object has been moving through the cosmos for millions of years, following a trajectory set in motion long before it ever approached our solar system. The journey of the new object is a reminder of the interconnectedness of the universe. While we tend to think of our solar system as an isolated unit, the reality is that we are part of a much larger cosmic network. Objects from outside our solar system pass through our neighborhood with relative frequency, and they carry with them the stories of the regions they have passed through. These objects are like cosmic messengers, delivering tidbits of information about the conditions that exist far beyond the boundaries of our own star system. Astronomers have known for some time that interstellar objects exist, but they have never had the opportunity to study one up close, until 3IATLAS made its appearance in 2017. That comet was the first confirmed interstellar object to pass through our solar system, and its discovery marked a turning point in our understanding of the universe. Now, with the discovery of this new object, we are faced with another opportunity to explore the unknown. What secrets does this new visitor hold? What can it teach us about the nature of interstellar space? Gravitational influence and path adjustments. As the new object moves closer to the sun, its path will inevitably be altered by the sun's immense gravitational pull. This is the law of gravity at work. As objects move closer to a massive body, they are accelerated, and their trajectories are bent. The closer the object gets to the sun, the more significant this effect will become. The new object's approach to the sun is a perfect example of this gravitational interaction. As it nears the sun, its speed increases dramatically. The sun's gravity tugs on the object, pulling it inward, and this causes its trajectory to shift. But this shift is not random. It follows a predictable pattern, one that can be calculated and measured with great precision. By tracking the object's movement as it gets closer to the sun, astronomers can learn more about its exact path and how it will be affected by the sun's gravity. At the moment of perihelion, when the object is closest to the sun, its speed will be at its highest. This is the point where the object's path will bend the most. The force of gravity will cause the object to accelerate to incredible speeds, and this increase in speed will allow it to continue on its journey through the solar system, eventually leaving our sun behind. For astronomers, the challenge is in predicting exactly how this process will unfold. While the laws of gravity are well understood, the precise path of an object like this is difficult to calculate. There are so many variables at play: speed, angle of approach, gravitational influence, and the nature of the object itself, that even small changes in one of these factors can have a significant impact on the object's trajectory. This is where the real art of astronomy comes into play: observing, calculating, and predicting the behavior of objects that are far beyond our immediate reach. The role of solar wind and light pressure. As the object approaches the sun, another factor comes into play: the sun's solar wind. The solar wind is a stream of charged particles that flows outward from the sun, carrying with it energy and momentum. While the solar wind is not strong enough to significantly affect large bodies like planets or asteroids, it can have an impact on smaller objects, especially comets. If the new object is a comet, the solar wind will have a noticeable effect on its tail. The solar wind pushes on the gas and dust that is ejected from the object, causing the tail to point away from the sun. This is why the tails of comets always point in the opposite direction of the sun, regardless of the object's direction of travel. This behavior is one of the defining characteristics of a comet and is a result of the interaction between the object and the sun's solar wind. Similarly, light pressure from the sun will also play a role in the object's behavior. Light pressure is the force exerted by sunlight on an object, and while it is very small, it can still have an effect on an object's trajectory. For comets, the pressure of light can cause their orbits to shift slightly, especially if the object is small and lightweight. The light pressure also contributes to the release of gas and dust from the comet's surface, creating the bright, glowing coma and tail. These forces, solar wind and light pressure, are subtle but important. They can alter the trajectory of the object, push on its tail, and even affect its rotation. For a comet, this can lead to changes in its appearance as it approaches the sun, with the tail growing larger and brighter as the object releases more gas. For an asteroid or other non-gaseous object, the effects may be less noticeable, but they still play a role in shaping the object's journey. The future path, leaving the solar system. Once the object passes perihelion, the closest point to the sun, it will begin to move away again. The sun's gravity will no longer be able to accelerate it in the same way, and the object will gradually lose speed as it moves farther from the sun. Eventually, the object will leave the solar system entirely, continuing its journey into the vast expanse of interstellar space. While the object will no longer be in our neighborhood, its journey will not be forgotten. The data gathered from its passage through the solar system will be analyzed for years to come, providing valuable insights into the behavior of interstellar objects and the conditions that exist in other star systems. In the future, astronomers will continue to study this object's trajectory, analyzing how its path was altered by the sun's gravity, the solar wind, and light pressure. They will use this data to refine their models of interstellar object movement and gain a deeper understanding of the dynamics of our galaxy. The object's departure from the solar system will mark the end of its brief visit to our corner of the universe. But just because it is leaving doesn't mean it is forgotten. It will continue to travel through the galaxy, its journey a quiet testament to the forces that govern the motion of objects in space. And while it may never return, its passage has left an indelible mark on our understanding of the cosmos. The bigger picture. The story of this object's journey is a reminder that the universe is far from empty. Interstellar objects, comets, asteroids, and other bodies travel through the vast expanse of space, some of them coming into our solar system for a brief visit, others passing by unnoticed. Every new discovery, every new object brings with it a piece of the puzzle that helps us understand the broader workings of the universe. The path this object has taken, from the far reaches of interstellar space to the warm embrace of the sun, is a story of cosmic dynamics, of gravitational forces, light pressure, and the eternal movement of objects through space. And while this object may leave our solar system, its journey is far from over. It will continue on, carrying with it the echoes of its passage through our star system, reminding us that we are part of a larger, ever-expanding cosmos. And so, as this object races toward the sun and then continues on its way, we are left with the knowledge that the universe is filled with stories waiting to be told. Every object that passes through our solar system, whether it's a comet, an asteroid, or an interstellar visitor, is a reminder of the vastness of space and the ever-changing nature of the cosmos. For now, we watch and wait, knowing that the next discovery is just around the corner, ready to reveal another secret of the universe. As we approach the center of our investigation into the new object racing toward the sun, we find ourselves reflecting on the intricate dance of forces, the mysteries that are slowly being unraveled, and the uncharted paths these celestial bodies follow. While much of the excitement surrounding this object has been focused on its speed, composition, and its eventual departure from our solar system, there is another equally intriguing aspect of this cosmic visitor that warrants our attention, what we almost missed. As the object continues its path toward the sun, astronomers are collecting invaluable data on its behavior and characteristics. Yet, just as in every other realm of science, the discovery of an object like this raises more questions than it answers. In fact, some of the most profound insights come not from what we can immediately see, but from what we almost overlook: the small anomalies, the subtle changes, and the clues hidden just out of sight. Sometimes, the most significant pieces of the puzzle are the ones that slip through the cracks, barely noticeable to the untrained eye, yet capable of shifting our understanding of the universe. In this chapter, we focus on these overlooked details, the hidden clues, and the things we almost missed during the discovery and observation of this new interstellar visitor. As astronomers sift through the data collected from telescopes and observatories, they continue to find things that were not initially apparent. These small findings can have enormous implications for our understanding of the object's origin, behavior, and potential impact on our solar system. The invisible forces at play. When astronomers first began tracking this new object, they relied on their primary tools: powerful telescopes, precise measurements, and careful calculations. The object's trajectory, its speed, and its movement through space were all mapped with great accuracy, giving us a clear picture of its journey. But what about the forces that cannot be easily measured? What about the subtle effects that influence the object's path without being immediately apparent? One of the most fascinating aspects of studying objects like this one is understanding the invisible forces that shape their motion. We often think of space as empty, but in reality, it is far from it. Between the stars, there is a faint but constant pressure from cosmic radiation and interstellar dust, as well as the magnetic fields that stretch across vast distances. While these forces are weak compared to the gravitational pull of stars and planets, they can still have a profound impact on the motion of small objects, especially those that are moving at high speeds. For the new object racing toward the sun, the subtle forces at play are often difficult to detect. The object's speed, trajectory, and composition can all be measured with precision, but the effects of cosmic radiation, dust, and magnetic fields are far less obvious. As astronomers study the object's path, they must account for these unseen factors, which can influence its trajectory in ways that are not immediately noticeable. This is where the role of advanced computer modeling comes into play. By simulating the object's journey through space, astronomers can better understand the subtle forces that are shaping its path. These models take into account not only the well-understood forces of gravity and light pressure, but also the lesser-known influences that can cause objects to drift off course. For example, the object's interaction with cosmic dust could cause it to slow down ever so slightly, or a shift in the magnetic field could subtly alter its direction. While these changes may seem small, they can accumulate over time, affecting the object's trajectory in ways that are difficult to predict. The role of solar wind and outgassing. In the case of comets, one of the most significant forces at play is the solar wind. The solar wind is a constant stream of charged particles emitted by the sun, which travels outward through the solar system at speeds of around 400 kilometers per second. When comets pass close to the sun, the solar wind interacts with their icy surfaces, causing gases to be released and forming a visible tail. For a comet like 3IATLAS, this process was quite obvious. Its tail formed as it neared the sun, visible from Earth as a bright, glowing stream of gas and dust. However, for the new object racing toward the sun, there has been little evidence of such outgassing. This could be due to the fact that the object is not a typical comet, but rather a rocky asteroid, or perhaps it is simply not close enough to the sun yet to begin the outgassing process. Yet even without visible outgassing, the solar wind still exerts an effect on the object. This invisible force can slightly alter the object's trajectory, pushing it in a direction that is not fully accounted for by gravitational forces alone. It's a subtle effect, but one that astronomers must consider when calculating the object's future path. As the object gets closer to the sun, the intensity of the solar wind will increase, and its influence on the object may become more pronounced. Astronomers are particularly interested in studying this interaction because it could reveal important information about the object's composition. If the object were to begin releasing gas and dust, it could provide a glimpse into its internal structure, whether it is icy or rocky, whether it has volatile materials that could be released under the heat of the sun. Even though we have yet to see a dramatic outgassing event, this subtle interaction with the solar wind is an important clue that should not be overlooked. The importance of small observations. In astronomy, small observations can have a disproportionately large impact. It is often the tiniest details that change the course of scientific understanding, turning a simple observation into a groundbreaking discovery. When studying objects like the new interstellar visitor, astronomers must pay close attention to these small details, especially in the early stages of observation. For example, the object's brightness and reflectivity can reveal important information about its surface. A slight change in brightness could indicate the presence of gases or dust being released from the object, or it could signal a change in the object's rotation. Similarly, subtle shifts in the object's trajectory, caused by forces like solar wind or radiation pressure, can provide astronomers with valuable data about the object's composition and the environment it originated from. In some cases, these small observations can lead to unexpected discoveries. For example, astronomers may notice that the object's trajectory has been altered by an unseen force, leading them to investigate further. This could result in the discovery of new phenomena or forces that were previously unknown, offering a fresh perspective on the workings of the universe. The cosmic tapestry, what we missed in the larger picture. When we look at the universe, we often focus on the big, dramatic events, the discovery of new planets, the collision of galaxies, the birth and death of stars. These moments are awe-inspiring, and they provide the material for much of our scientific understanding. But the universe is not just made up of these grand spectacles. It is also composed of countless smaller interactions, subtle, often imperceptible forces that shape the motion of objects and the development of cosmic structures. The new object racing toward the sun is a perfect example of this larger tapestry. It is not just a single object. It is a part of a much larger cosmic network. Its journey through the solar system, its interaction with the sun and its solar wind, its trajectory through interstellar space, all of these factors are connected to a broader, deeper system of cosmic forces. While the object itself may be a small blip in the grand scale of the universe, its passage through our solar system provides a rare opportunity to observe the intricate workings of these forces up close. And it's not just about what the object reveals about itself. By studying its passage, we learn more about the processes that govern the behavior of all objects in the universe, from the formation of stars and planets to the way that gravity and light pressure shape the paths of interstellar visitors. We gain insight into the conditions that exist in other parts of the galaxy and beyond, helping us refine our models of cosmic dynamics. Conclusion: what we almost missed. In the study of space, what we almost miss often holds the key to our greatest discoveries. The new object racing toward the sun is a reminder that even the smallest details, the subtle shifts in trajectory, the faint glimmers of outgassing, the minute changes in brightness, can provide invaluable clues about the object's nature and origins. As astronomers continue to gather data and refine their observations, they will uncover even more of the hidden story behind this cosmic traveler. What we almost missed is often what pushes the boundaries of our knowledge, forcing us to rethink our assumptions and expand our understanding of the universe. Every small observation is a step closer to uncovering the greater mysteries of the cosmos, and every new discovery is a reminder that the universe is far more complex and interconnected than we could ever imagine. In the quiet, expansive void of space, where stars blink in and out of view, and the silent passage of comets is barely perceptible to the naked eye, the story of a single object racing toward the sun might seem like an insignificant event. But for astronomers, the very act of observation is a profound reminder that the universe is always alive with motion, transformation, and mystery. The arrival of a new object from interstellar space is a cosmic event in and of itself, an opportunity to study forces beyond our solar system, forces that we have only begun to understand. In this chapter, we'll explore what happens when an object from outside our solar system begins to approach the sun, when the deep cold of interstellar space gives way to the warmth and radiation of our star. As objects move closer to the sun, they experience a host of physical and chemical changes, some of which are subtle and others that are dramatic. From the ice and dust of a comet's nucleus to the electromagnetic forces that shape the object's tail, the interaction between the interstellar visitor and the sun is one of the most fascinating processes in the cosmos. Here, we take a closer look at how the object's proximity to the sun might change its behavior, what astronomers can learn from these changes, and how they study these interactions to uncover new insights into the nature of the object itself. As the object gets closer, it enters a region of the solar system where forces like gravity, radiation, and solar wind all come into play. Together, these forces will guide its path, determine its appearance, and help astronomers piece together its story. Observing the object in detail, a unique opportunity. When an interstellar object like this one is discovered, astronomers are eager to study it up close. But because these objects tend to move quickly through the solar system, time is of the essence. Once an object like this one is spotted, astronomers must carefully track its movements, watching it as it races toward the sun. However, there is a brief window of time in which this object will be close enough for detailed observation, and this moment of opportunity is invaluable. The challenge is not just in observing the object, but in understanding the different ways in which it interacts with the solar system. The object is a stranger in our cosmic neighborhood, and as it approaches the sun, it will experience a range of phenomena that are unique to our solar system. This is why astronomers rely on a range of tools to observe the object, tools that can provide a snapshot of its behavior as it reacts to the sun's gravitational pull, solar radiation, and the solar wind. One of the primary methods of observing such an object is through telescopic observations. Ground-based and space-based telescopes are constantly scanning the sky for moving objects, and once the new visitor was discovered, scientists began to monitor it with a keen eye. The power of modern telescopes allows astronomers to detect the faintest of light signals from an object millions of kilometers away, providing a wealth of data that can reveal everything from the object's size and shape to the materials that make up its surface. Through careful observation, astronomers can track the object's speed and trajectory, noting how it accelerates as it approaches the sun. By comparing this information with models of gravitational interactions, they can learn more about the object's path and predict where it will go once it leaves the solar system. At the same time, they are able to monitor the object's brightness and any changes in its light signature. These changes can indicate whether the object is releasing gas or dust, as would be expected if it were a comet, or if it is a more solid body, like an asteroid, that is not undergoing the same kind of outgassing. Solar wind and outgassing, the role of the sun's energy. As the object gets closer to the sun, it begins to experience the full effects of solar radiation. The sun's energy is not just a source of light and heat for our planet. It is a constant force that impacts every object within the solar system. For comets, the sun's heat causes their icy nuclei to sublimate, releasing gas and dust into space. This process, known as outgassing, creates the coma and tail that we associate with comets. If the new object racing toward the sun is indeed a comet, then astronomers are eager to observe the changes in its tail as it nears the sun. The sun's heat will cause the object's surface to heat up, releasing volatile gases like water vapor, carbon dioxide, and ammonia. As the object continues to move closer to the sun, the gas released from its nucleus will be pushed outward by the solar wind, forming a tail that always points away from the sun. This is a defining characteristic of comets, and it provides astronomers with valuable clues about the object's composition and behavior. Even if the object is not a typical comet, perhaps it is a rocky body or an asteroid, the sun's radiation still has an effect. Solar radiation exerts pressure on all objects in the solar system, no matter how small or large. This pressure is called solar radiation pressure, and it is a result of the sun's photons striking the object and transferring momentum to it. For large bodies, this pressure is negligible, but for small objects like comets and asteroids, it can have an impact on their trajectory. In the case of this interstellar object, astronomers are paying close attention to how the sun's radiation might alter its path. The closer it gets to the sun, the stronger the effect of solar radiation pressure will be, and this could slightly change the object's trajectory, pushing it off course. In addition, if the object is composed of volatile materials, the outgassing process could also create small, localized jets that alter the object's rotation or direction. What we can learn from the tail. If the object does indeed exhibit outgassing as it nears the sun, astronomers will have a unique opportunity to study its tail and coma in greater detail. The tail of a comet is not just a glowing streak of light in the sky. It is a complex collection of gas, dust, and particles that tell us about the object's composition, its activity, and its history. By studying the tail of an interstellar comet, astronomers can learn more about the material that makes up the object, the temperature and pressure conditions inside its nucleus, and the processes that occur as it interacts with the solar wind and solar radiation. The composition of the tail can also reveal information about the object's origin. If the object is a comet, the presence of certain gases or organic compounds could suggest that it originated from a region of space rich in these materials. This would provide valuable insights into the conditions that exist in other star systems and the processes that lead to the formation of comets. If the object is more asteroid-like, with little to no outgassing, its tail may be less pronounced, but its surface features will still provide important clues about its composition. Through careful analysis of the tail and coma, astronomers can build a more complete picture of the object's nature. They can compare its behavior to other known comets and asteroids, looking for patterns and differences that might reveal new information about the physical processes that govern these objects. In this way, the tail of the object becomes more than just a visual phenomenon. It becomes a key to unlocking the secrets of the object's origin, its composition, and the forces that have shaped it. The importance of close observation. As the object races closer to the sun, the importance of close observation becomes even more critical. The object is moving through an area of space where the effects of the sun's radiation, solar wind, and gravitational forces are most pronounced. This is the region where astronomers can gather the most detailed data about the object's behavior, its changes, and its interactions with the sun. Every small shift in its trajectory, every tiny alteration in its brightness, and every change in its tail provides astronomers with new information that can help us understand more about the universe. For astronomers, this is a race against time. As the object moves closer to the sun, it will eventually pass beyond the point where we can observe it directly. Once it moves out of the solar system, its path will become too difficult to track, and its light will become too faint for telescopes to capture. This is why it's so important to study the object in the brief window of time when it is close enough to observe in detail. The data collected during this period will help astronomers refine their understanding of interstellar objects and their behavior as they travel through our solar system. While we may never fully understand the origins of this mysterious visitor, the observations made during its brief passage through our solar system will help us make sense of the cosmic forces that shape the objects we see in the sky. The object's interaction with the sun, its behavior, and the changes it undergoes as it moves through our solar system will provide valuable insights into the dynamics of our galaxy and the broader universe. looking toward the future. As we watch this object make its way toward the sun, we are reminded that the universe is filled with mysteries that are waiting to be uncovered. The study of interstellar objects, comets, and asteroids provides us with a glimpse into the processes that have shaped the solar system and the galaxy, and each discovery adds to our understanding of the universe as a whole. The new object racing toward the sun, like 3IATLAS before it, is a reminder that the cosmos is always moving, always changing, and always revealing new secrets. As we continue to study these objects, we are not only learning about their individual stories, but also about the larger forces at play in the universe, forces that connect us all to the stars. In every corner of the universe, from the farthest galaxies to the smallest particles of dust drifting through space, there are stories waiting to be uncovered. The study of these stories, whether they involve the birth of stars, the movement of planets, or the behavior of comets, takes us on a journey of discovery that is as humbling as it is exhilarating. But when we encounter an object from another star system, like the one racing toward the sun, we are reminded that our solar system is but one small part of a vast interconnected cosmos. Each interstellar visitor is a messenger, carrying with it clues that help us piece together the larger puzzle of the universe. In this chapter, we will examine the different theories and models that scientists have proposed to explain the behavior of interstellar objects like this one. By studying their movements, their compositions, and their interactions with the sun and other celestial bodies, astronomers can refine their understanding of the forces at play in the cosmos. While we may never fully understand where these objects come from or where they are headed, the study of their paths offers us an opportunity to probe the mysteries of interstellar space and the dynamics of our galaxy. Theories of interstellar object origins. When astronomers first discovered 3IATLAS in 2017, the scientific community was confronted with a question that had never been asked before. Where do interstellar objects come from? While the solar system has long been studied as a closed system, with planets, comets, and asteroids all born from the same disk of gas and dust around the sun, the discovery of an object from another star system shattered this assumption. For the first time, scientists were able to observe a celestial object that had traveled across the vast expanse of interstellar space before arriving in our solar system. Theories about the origin of these objects have evolved as more data has been collected. Some astronomers propose that these interstellar visitors come from the dense molecular clouds that exist in the space between stars. These clouds are vast regions of gas and dust where new stars are born. Within these clouds, the conditions are right for the formation of small, icy bodies, comets, asteroids, and other objects. When a star forms and begins to exert its gravitational influence on its surroundings, some of these objects are ejected from their birthplaces, sent on trajectories that carry them across interstellar space. Another theory suggests that interstellar objects may come from the outskirts of star systems, where the gravitational influence of the parent star is weaker. In these regions, objects can be perturbed by the gravitational forces of nearby stars, sending them into interstellar space. These objects could then travel for millions or even billions of years before eventually being captured by the gravitational pull of a new star system, like our own. Regardless of their origin, one thing is clear: interstellar objects are not rare. They are more common than we once thought. While 3IATLAS was the first confirmed interstellar object, astronomers now believe that many more objects like it are passing through the solar system. their trajectories influenced by the gravitational forces of stars and planets. Some of these objects may never be detected, but others, like the new visitor racing toward the Sun, offer us a rare opportunity to study the behavior of these interstellar travelers. Models of object behavior in the solar system. One of the key challenges in studying interstellar objects is understanding how they behave as they move through the solar system. While we can observe their trajectories and study their compositions, the dynamics of their interactions with the Sun, the planets, and the solar wind are complex. Over the years, scientists have developed models to predict how these objects will behave, but the unique characteristics of each object make it difficult to apply a one-size-fits-all approach. The first model that scientists use to study the behavior of interstellar objects is based on the laws of gravitational physics. According to these laws, the Sun's gravity will pull an object toward it, altering its path and increasing its speed as it approaches perihelion, the point of closest approach. This effect is well understood, and astronomers can use this model to predict the object's speed and trajectory as it moves through the solar system. However, this model only accounts for gravity. It doesn't take into consideration other factors, such as the influence of the solar wind, light pressure, or outgassing from comets. To account for these additional forces, astronomers have developed more complex models that incorporate these factors. For example, the solar wind can push on small particles, creating a drag that alters their trajectory over time. Similarly, light pressure can cause a comet's tail to point away from the Sun, influencing the object's motion. One of the most important aspects of studying interstellar objects is understanding how they interact with the Sun's radiation. The Sun emits not only light, but also a constant stream of charged particles known as the solar wind. As an object moves through this wind, it experiences a force that can slightly alter its path. While this effect is subtle for large objects like planets, it can be more pronounced for small bodies like comets and asteroids. For example, the tail of a comet is pushed away from the Sun by the solar wind, and the outgassing of the comet creates additional momentum that can further affect its trajectory. Another important factor to consider is the influence of the planets. While the Sun's gravity is the dominant force acting on interstellar objects, the gravitational pull of planets like Jupiter can also have an impact. These planetary encounters are not always predictable, and the gravitational influence of a planet can alter an object's path in ways that are difficult to model accurately. In the case of the new object racing toward the Sun, it is possible that its trajectory will be affected by the gravitational forces of the outer planets as it moves through the solar system. These interactions are difficult to predict, but they add another layer of complexity to the study of interstellar objects. Comparing theories: interstellar comets versus asteroids. As we continue to study the new object racing toward the Sun, one of the key questions that arises is whether it is a comet or an asteroid. This distinction is important because comets and asteroids behave in different ways, and their compositions are fundamentally different. Comets are icy bodies that are composed of water, carbon dioxide, methane, and other volatile compounds. When they approach the Sun, the heat causes these compounds to sublimate, creating a coma and tail. Asteroids, on the other hand, are rocky bodies that do not exhibit the same outgassing behavior. The question of whether the new object is a comet or an asteroid has significant implications for our understanding of its origin. If the object is a comet, it would suggest that it originated from a region of space that is rich in volatile materials, perhaps from a molecular cloud or the outer reaches of a star system. If the object is an asteroid, it might be a remnant of a planetary system that failed to form a full-fledged planet, or it could be an object that was ejected from a distant star system and sent on a journey across interstellar space. The new object's behavior so far suggests that it may be more comet-like than asteroid-like. While it has not yet shown dramatic outgassing, its high speed and trajectory indicate that it may be composed of volatile materials that could vaporize as it approaches the Sun. However, scientists will need to observe the object more closely as it gets closer to the Sun in order to confirm this theory. If the object begins to display the classic signs of cometary outgassing, such as the formation of a coma or tail, then it will become clear that it is a comet and not an asteroid. The study of whether this new object is a comet or an asteroid will provide us with important clues about the conditions in other star systems. If it is a comet, it could be a sample of the icy bodies that populate the outer regions of star systems, providing valuable information about the materials that are present in the coldest parts of space. If it is an asteroid, it could offer insights into the rocky remnants of failed planets or planetary building blocks in other star systems. Either way, the object offers a rare opportunity to study the composition and behavior of an interstellar visitor up close, refining our models of interstellar object behavior. As we continue to study the new interstellar visitor, we are forced to confront the limitations of our current models. While scientists have developed sophisticated models to predict the behavior of interstellar objects, these models are not perfect. Each new discovery adds another layer of complexity to our understanding, and sometimes the data we collect forces us to rethink our assumptions. The new object racing toward the Sun is a perfect example of this. Its high speed, unusual trajectory, and potential outgassing behavior present a challenge to our existing models. For example, if the object is indeed a comet, we will need to refine our understanding of how these objects behave when they come from outside our solar system. If it is an asteroid, we will need to consider the ways in which the Sun's radiation and the gravitational influence of the planets might alter its path. Every new observation of this object will help refine our models and improve our ability to predict the behavior of interstellar objects in the future. By studying its path, its composition, and its interactions with the solar wind and radiation, astronomers will be able to update their models and apply them to future interstellar visitors. These updates will not only improve our understanding of objects like the new visitor racing toward the Sun, but also help us better understand the dynamics of interstellar space and the broader processes that govern the movement of objects through the galaxy. Looking ahead, the legacy of interstellar exploration. The study of interstellar objects is still in its early stages, but already it has yielded valuable insights into the nature of the universe. Objects like 3IATLAS and the new visitor racing toward the Sun are cosmic messengers, carrying with them the secrets of distant star systems. As we continue to observe these objects and refine our models, we will gain a deeper understanding of the forces that shape the universe and the conditions that give rise to the stars, planets, and comets that populate it. The discovery of interstellar objects is not just a scientific curiosity. It is a reminder that the universe is much larger and more interconnected than we ever imagined. Objects from distant star systems pass through our solar system, offering us a glimpse into the conditions that exist far beyond our own corner of the galaxy. As we continue to study these objects, we will not only learn more about their origins and behavior, but also gain a better understanding of the forces that shape the cosmos. The new object racing toward the Sun is just one piece of this larger puzzle. It is a brief visitor, but its passage through the solar system is a reminder that the universe is full of surprises and that the story of our galaxy is still unfolding. As we continue to explore the cosmos, we are reminded that there is always more to learn, more to discover, and more to marvel at in the great expanse of space. As the new interstellar object continues its journey through the solar system, astronomers and scientists alike are eagerly watching, tracking, and analyzing its every movement. While the object's passage through our solar system is a fleeting event, it offers us a rare and valuable opportunity to observe the forces that shape the universe and the behaviors of objects that come from beyond our star system. Yet, in the pursuit of knowledge, it is crucial that we don't simply focus on what we already know, but that we also confront what we don't know, what is still hidden from view. The more data we collect, the more questions arise. What's truly behind the behavior of the object? What forces are shaping its path? What mysteries does it hold that have yet to be uncovered? In this chapter, we will dive into the limits of our current understanding, addressing the unanswered questions, acknowledging the boundaries of our knowledge, and exploring the unknowns that still linger as the object passes through our solar system. Even with the most advanced technology and methods at our disposal, there remain gaps that we can only begin to imagine filling. But these gaps are what drive the scientific process forward. They compel us to refine our theories, develop new models, and explore new frontiers in our quest for understanding. The unknowns of interstellar objects. When an object from interstellar space enters our solar system, it is, in a sense, a cosmic anomaly. Everything about it, its speed, its trajectory, its composition, poses questions that have never been asked before. While we can calculate the object's orbit and track its movement, the deeper mysteries about its nature remain elusive. The problem is not that we lack the tools to observe. Rather, the challenge lies in the complexity of the forces at play, forces that we cannot fully predict. One of the first unknowns is the exact origin of the object. While astronomers can observe its trajectory and calculate its speed, the true birthplace of the object remains a mystery. Is it part of a distant planetary system, sent out into the void by a wandering star? Or is it an ancient relic from the early days of the galaxy, a piece of cosmic debris that has drifted through interstellar space for millions of years before it was captured by the gravitational pull of our sun? These are questions that can only be answered through further study and observation, and even then, the answers may remain elusive. The composition of the object is another significant unknown. While we have some ideas about the types of materials it may contain based on its behavior and initial observations, the true nature of its surface and its interior is still a mystery. Is it made of the same icy compounds that make up the comets in our own solar system? Or is it composed of denser, more rocky materials, like many asteroids? The data we have so far is inconclusive, and the object's composition may not be fully revealed until it gets closer to the sun, or until its passage is complete. Beyond its composition and origin, there are also questions about the object's behavior. For example, how will it react to the sun's radiation? Will it display outgassing behavior as it approaches perihelion, forming a bright coma and tail? Or will it remain more stable, like an asteroid, with no visible outgassing? These questions remain unanswered, and as the object draws closer to the sun, astronomers will continue to monitor its activity, hoping to gain new insights. The limits of current technology. One of the greatest challenges in studying objects like this interstellar visitor is the limitations of our current technology. While we have made tremendous strides in the field of astronomy, Many of the tools we use to observe distant objects are still in their infancy, and there is only so much that we can learn with the instruments available to us today. Space telescopes like Hubble and ground-based observatories are incredibly powerful, but they are not perfect. They are limited by their sensitivity, their resolution, and their ability to detect objects that are millions of kilometers away. When the new object was first discovered, it was still far from the sun, and it was difficult to study in great detail. As it moves closer, astronomers will be able to refine their observations, but by the time the object reaches its closest point to the sun, perihelion, much of the information will already be out of reach. The object's fast-moving nature makes it especially difficult to track, and once it has passed through the inner solar system, it will quickly move beyond the reach of our telescopes. While astronomers are doing their best to capture as much data as possible, there is always the chance that key details will slip through the cracks. For example, subtle changes in the object's brightness or trajectory could indicate something important about its composition or its behavior. But these changes are often hard to detect amidst the noise of other cosmic phenomena. The true nature of the object may remain just out of reach, and we may only be able to glimpse a fraction of the story it has to tell. What we can't see, cosmic interactions beyond our view. In addition to the limitations of our technology, there is also the reality that some of the forces acting on the object are invisible to us. While we can study its surface and its tail, we are still blind to some of the more subtle interactions that take place between the object and the surrounding environment. For example, we can't directly observe the effect of cosmic rays on the object, or how it might interact with the faint magnetic fields that pervade interstellar space. These forces, while not immediately visible, still have an effect on the object's behavior, and understanding them is key to gaining a complete picture of its journey. In a similar vein, we are limited in our ability to study the object's long-term trajectory. While we can predict its path through the solar system with great accuracy, its future path beyond the solar system remains uncertain. Objects like this one can travel vast distances through interstellar space, and once they leave our solar system, their path becomes more difficult to track. The forces that will influence their trajectory once they are far from the sun are harder to predict, and much of the journey remains a mystery. The limitations of our understanding of the solar system. While we know a great deal about the solar system, its planets, its moons, and its comets, there is still so much that remains unexplored. The outer reaches of the solar system, where objects like this interstellar visitor come from, are still largely a mystery. The Kuiper Belt and Oort cloud, the distant regions of space where many comets originate, remain unexplored by spacecraft, and much of what we know about them is based on indirect observations. Even closer to home, there are many questions that remain unanswered. For example, how do the outer planets and their moons interact with the solar wind and the interstellar medium? How do objects from outside the solar system affect the behavior of bodies within the solar system? These questions remain largely unexplored, and the study of interstellar objects like this one offers a rare opportunity to gain insight into these hidden regions of space. As we continue to explore the solar system and beyond, we will inevitably encounter new questions, new challenges, and new mysteries. The discovery of interstellar objects like 3IATLAS and the new object racing toward the sun is just one example of how the universe constantly surprises us with new opportunities for discovery. But these discoveries also highlight the limits of our current knowledge. We may never have all the answers, but it is precisely the unknowns that drive us forward, propelling us to explore deeper, think bigger, and strive for a better understanding of the cosmos. The future of interstellar exploration. While our current understanding of interstellar objects is still in its early stages, the future of interstellar exploration is incredibly exciting. With advancements in technology, new space missions, and improved observation techniques, we are entering an era of discovery that will allow us to explore objects from beyond our solar system in unprecedented detail. In the coming years, we will continue to refine our models of interstellar object behavior, develop more sophisticated tools for observing distant objects, and launch new missions to study the outer reaches of the solar system. The future holds the promise of new discoveries, new insights, and new frontiers in our understanding of the universe. And while we may never fully uncover all the mysteries of objects like the new visitor racing toward the sun, each new discovery will bring us closer to understanding the true nature of the cosmos. Conclusion: embracing the unknown. As we watch the new interstellar object race toward the sun, we are reminded that the universe is full of unknowns, forces, behaviors, and phenomena that we can only begin to understand. In the pursuit of knowledge, there is always more to discover, and every new discovery opens up new questions and new avenues for exploration. While we may never have all the answers, it is the journey of discovery that keeps us moving forward, propelling us into the unknown with curiosity, wonder, and a sense of awe. The limits of our knowledge should not discourage us. Rather, they should inspire us to keep pushing the boundaries of what we know. The discovery of interstellar objects like 3IATLAS and the new visitor racing toward the sun is a reminder that the universe is vast, dynamic, and full of surprises. And as we continue to explore the cosmos, we are reminded that the greatest discoveries are often the ones that lie just beyond the reach of our understanding, waiting for us to uncover them, piece by piece, as we continue our journey through the stars. As we come to the final chapter of this exploration into the mysterious interstellar object racing toward the sun, we step back and reflect on everything we've learned, the questions that remain unanswered, and the incredible journey this object has taken from the far reaches of interstellar space to the heart of our solar system. The object's brief passage through our solar system has been a reminder that the universe is full of surprises, and that every discovery, no matter how fleeting, brings us closer to understanding the grand mysteries of the cosmos. The story of this object is not just a tale of an interstellar visitor, but a reminder of the vastness of the universe, the interconnectedness of everything within it, and the ways in which we are all linked through the forces that govern the cosmos. The object's journey, from its distant origin to its high-speed passage through the solar system, is a testament to the incredible complexity of space, time, and gravity. And as it moves on, leaving our solar system behind, it will carry with it the data and insights that will help scientists refine their understanding of the universe and continue the quest for knowledge. The significance of the discovery. At the heart of this discovery lies a fundamental question. What does this object teach us about the nature of the universe? The discovery of interstellar objects like 3IATLAS and this new visitor forces us to reconsider the idea of our solar system as an isolated, self-contained unit. In reality, our solar system is part of a much larger, dynamic universe, where objects move freely between star systems, shaped by forces that we are only beginning to understand. These interstellar visitors are like cosmic messengers, bringing with them clues about the conditions that exist in other parts of the galaxy and beyond. Through the study of these objects, we are learning more about the materials that make up the building blocks of stars and planets, the processes that govern the formation of planetary systems, and the dynamics of the interstellar medium, the space between the stars that is often invisible to our eyes. The data we gather from these objects is invaluable in helping us understand the bigger picture of how our solar system fits into the broader context of the galaxy and the universe. But perhaps the most profound lesson we can take from this discovery is the realization that we are just beginning to scratch the surface of what is possible. The universe is vast, and there is so much more out there to explore. Each discovery, each new object that passes through our solar system is an opportunity to deepen our understanding and expand our knowledge. And even though we may never fully understand the origins of objects like the new visitor racing toward the sun, the pursuit of knowledge itself is a journey worth taking. Looking forward, the future of cosmic exploration. As we reflect on the lessons learned from this interstellar visitor, it's impossible not to think about the future of cosmic exploration. The study of interstellar objects is still in its early stages, but already it has begun to reshape our understanding of the universe. With advancements in technology, better telescopes, and future space missions, we are entering a new era of discovery, one that will allow us to study objects from beyond our solar system in unprecedented detail. The future holds the promise of even more interstellar objects, each one offering new insights into the forces and conditions that shape the universe. In the coming years, astronomers and scientists will continue to refine their models of interstellar object behavior, develop new techniques for observing distant objects, and design missions to explore the far reaches of the solar system and beyond. Already we are seeing the first glimpses of interstellar exploration with missions like NASA's Voyager probes, which are traveling beyond the outer reaches of the solar system, carrying with them messages to future generations. As technology continues to improve, we will be able to observe objects like the new visitor in greater detail, tracking their movements with precision and analyzing their composition with advanced instruments. The data collected from these objects will help us understand not only the objects themselves, but also the larger cosmic forces that govern their behavior. We will continue to probe the mysteries of interstellar space, expanding our knowledge of the universe and our place within it. The infinite possibilities of discovery. One of the most exciting aspects of scientific exploration is the constant sense of discovery. No matter how much we learn, there is always more to uncover. Each new object that enters our solar system, each new discovery in the cosmos, opens up new possibilities for understanding. The study of interstellar objects is just one example of this. These objects may seem small or insignificant, but they hold the key to unlocking some of the deepest mysteries of the universe. As we continue to study objects like this one, we will gain a better understanding of the processes that govern the formation of stars and planets, the nature of interstellar space, and the conditions that give rise to life. We may even discover that objects like this new visitor hold clues about the origins of our own solar system, offering a glimpse into the distant past of our cosmic neighborhood. But perhaps the most exciting aspect of these discoveries is the realization that we are not alone in our quest for knowledge. The study of interstellar objects brings together scientists, astronomers, and researchers from all over the world, united by a common goal: to understand the universe and our place within it. As we work together, sharing data, ideas, and insights, we will continue to push the boundaries of human knowledge and expand our understanding of the cosmos, embracing the mystery. As this interstellar object moves beyond the reach of our telescopes and disappears into the depths of space, we are left with a sense of wonder and awe. The questions it raises, the insights it provides, and the mysteries it leaves behind all remind us of the beauty and complexity of the universe. And while we may never fully uncover the full story of this object, where it came from, what it is made of, and what it will become, we can take comfort in the fact that its visit has enriched our understanding of the cosmos. The object's passage through our solar system is a reminder that the universe is full of mysteries, some of which we have yet to uncover. Every discovery, no matter how small, adds to the tapestry of knowledge that we are weaving, a tapestry that will continue to expand as we explore the cosmos. And while the path of this particular object may have been short, its impact on our understanding of the universe will be long-lasting, helping to shape the future of cosmic exploration for years to come. In the end, the pursuit of knowledge is not just about finding answers. It's about embracing the mystery. It's about asking the big questions and being willing to explore the unknown, even when we don't have all the answers. As we look to the stars, we are reminded that the universe is vast, and the journey of discovery is never truly complete. There is always more to learn, always more to explore, and always more to discover. And as we continue this journey, we are not just exploring the cosmos. We are exploring ourselves, our place in the universe, and the infinite possibilities that lie ahead.